Welcome to this colloquium, so prepared in the framework of the Physics for Development program organized by the Forum of International Physics, so as the APS, the American Physical Society. So first, I would like to introduce the member of our panel. So my name is Christine Dorf, so I work at the European Spallation Source in Sweden. I'm the vice chair of the FIP. We have Luisa Cifarelli from Bologna University, Italy, who is the co-chair or the past chair, sorry, of the FIP and the creator also and inspiration for this series, Physics Matters. We have also here present with us, so Joe Animela from the ICTP in Italy, who is the FIP elected chair. We have Alan Hurt, who is from Los Alamos in the US, who is the current FIP chair, and Marilena Longobardi from the University of Geneva, who is the FIP newsletter editor. So I want to pay a special attention as well to our co-host today. So we have, so beyond our team FIP, so the honor to be seconded by Professor Hafeez Hoorani from Pakistani, so sorry for the pronunciation. So he's from the National Physics Institute, and with his team, so Rabi Sharet, and Itishak Ahmad. So he will moderate as well the session and help us with this special event. So the purpose of our program, so this is to reach and engage developing community, so with inspiring topic in the field of physics. So we want to support international engagement, so among students, early career physicists, so targeting developing countries audience, but especially gathering inspiring physicists around the world. So we can see this from our website, and that we have selected some of the Sesame project to be able to co-host those live colloquia. So every month, so we are setting the scene mainly across the Middle East. So like in places like in Jordani, in Israel, in Iran, in Egypt, Turkey. And today, so we're going to travel to Istanbul. To Islamabad. So Istanbul will be next. So, so thanks to the magic of the internet, so we will first travel to Pakistan and have a short introduction by Professor Hafeez Hoorani. But before this, so I will zoom in the US, in Los Alamos, to introduce our guest speaker today, so who is Professor Linn. So he will warm us up with his knowledge about the common and devastating natural disaster that are wildfire. So to introduce, so Professor Linn, who is really a very important person in that field. He has a very long CV, but I will try just in a few words so to recall that he got his PhD in '97, so in the New Mexico State, on the topic of transport model for studying wildfire behavior. So he has been for more than 2 decades demonstrating some leadership in the field of wildfire behavior, modeling and application of coupled workfire and atmosphere behavior, modeling so the study, the fundamental behavior of wildfire, and the response to various environmental conditions. So he's an expert on theoretical turbulence, computational fluid mechanics, and heat transfer. He has been serving in many advisory capacity, many committee. He has been awarded, for instance, in 2003 with the R&D 100 award, so the Outstanding Technological Award in 2004. He's also associate editor of the International Journal of Wildland Fire, sorry. He's part of the board of the director in New Mexico State University, so in the mechanical engineering department, and also from the academic point of view, so he's a professor in the US Santa Barbara, and he had like this a long lasting award. So I will now introduce Professor Hafeez, who will give an introduction of the Islamabad Institute, and after that, so Linn will speak for about 45 minutes. So in the meantime, even during this presentation, you can put your questions in the chat box, which is available on your screen. And after the talk, so we'll get the possibility to gather those questions and to engage more into the discussion. So if Professor Azef could now share his screen and we can
Yeah,
listen about Islamabad.
sure. Fine. I will try to be brief, but before I start talking about my center, I would like to really thank American Physical Society and Forum on International Physics and the colleagues who have organized this. And I think this is a very interesting way of doing things, bringing people together from far away, and this way they can work together. So let me start with a brief introduction of National Center for Physics, which is located in Islamabad, Pakistan. This is northern part of Pakistan, and the vision of the center is really to evolve into a center of excellence in the area of physics, and would establish itself on the lines of Abdus Salam International Center for Theoretical Physics. So the initial idea was exactly the same, like a visitor-oriented center, and the aim of the center is to foster through training and research the progress of all branches of physics, especially paying attention to the needs of Pakistani universities and scientific and research and development organizations. These are some of our main functions, which includes R&D at the frontiers of science and technology, breaking the scientific isolation of the Pakistani scientists through scientific and training events. And that is where ICTP has always helped us a lot. And one of the persons sitting as panelist here, Professor Dr. Joe Nimela, he was very helpful. And he is, for him, NCP is the second home. Unfortunately, because of COVID, he's not traveling. Otherwise, he was a regular feature of our various events which were held in Pakistan at NCP. We also work establishing user-oriented research facilities that can be used at the national level. So at times I compare National Center for Physics with the national labs in US, where you develop a facility which cannot be established by one single group or a university, but it can be established by a consortium and by many groups together, uh, coming together and working for a common cause. We are doing human resource development in physics, producing or trying to produce high quality scientists, supervising postgraduate students, even though we ourselves are is not a university, not degree awarding, but we co-supervise and have links with the universities around us, and we get PhD students from them. We work on physics outreach and education, physics education particularly, and we are involved in international scientific cooperation, both eastward and westward. So, just to give you brief perspective in terms of history, uh, in fact, uh, the creation of NCP was a dream of Professor Abdul Salam, the only Nobel laureate from Pakistan in physics, and he established actually a center, of course, which he wanted to establish in Pakistan. But it so happened, due to a number of reasons, I cannot dwell into them right now, that he established it in Trieste, Italy in 1964. But he still proposed that a center similar to ICTP or a center for physics must be or should be established in Pakistan. He voiced this thing in 1986 in International Natia Gali Summer College. That was also his baby. And many top ranking scientists of Pakistan, they actually worked together along with the help of Professor Salam and after his demise as well to make it a reality. So the Nucleating Center for NCP was created at the university where I'm sitting, Quaid-e-Azam University in 1999. And Professor Riazuddin, a well-known theoretical physicist in particle physics, also one of the students of Professor Abdus Salam, joined as the first director of the center. The Nucleating Center initially was hosted in a very small building in the university, and that is the beginning. You see the building, a very small building, uh, and later on, uh, in 2000, the NCP, the real NCP, was inaugurated. At that time, we had a very close cooperation with CERN already. Professor Luciano Maiani, who was the Director General of CERN, he took part in the inauguration. You see some people standing very seriously and praying for something, including Professor John Ellis. Uh, Obviously, he's maybe also praying, but maybe something in a different way. You see Professor Riazuddin and some other people. Uh, then you see this, there is a signing of an agreement between Pakistan or between NCP and CERN. This was in 2000. And formally, NCP was established. The picture you see now, it looks like a very big complex, number of buildings. We are located on 20 acres of land. 20 acres, I don't know if you can understand this unit, but 1 acre is around 8,000 square meter. So if you multiply 20 acre of land, you can come up with the total number of square meter. And we are an autonomous institution in principle, at least on paper. We are reporting directly to the Prime Minister of Pakistan. But of course, in practice, it does not happen this way. Reporting to Prime Minister of Pakistan is not simple. But on paper, this is how it is. The building construction, which you see in the photograph above, was completed in 2007. Today, we have several departments. You see some names, some people. These are our directors of various departments. One is experimental high energy physics, nanosciences and materials, theoretical physics, ion beam physics, earthquake studies, vacuum science and technology, atomic and molecular physics lab. And then we have three other departments, which are support departments, collaboration and academic activities department, similar to Office of External Activities at ICTP. And we have administration and finance. Of course, we cannot live without them. These are the focus areas, broad areas. I did not spell out really exactly where we are working, such as astrophysics and cosmology, condensed matter physics, mathematical modeling and simulation, particle physics, plasma physics, quantum information and computing. These are the areas which we cover in theoretical physics. And then we have experimental part, which is advanced computing for scientific research, atomic and laser physics, experimental high energy physics, ion beam physics and applications, and nanoscience and technology. These are our focus areas of research. So just let me give you very quickly some numbers, and this will bring me to end of my talk. One is the number of papers we publish every year. So this plot shows the papers we have published starting from 2009 up to now, not necessarily up to now, almost end of last year. What you see in blue is the number of publication, and what you see in green is the impact factor. So with very few researchers, we are producing some good publications. And this fact can be seen or recognized by the Web of Science when they compared different R&D institute within Pakistan. We were ranked, if you look at category normalized citation impact based on the data up to 2020, we were ranked number one in Pakistan with 1.89 on this particular index. You five other institutes. I'm sure you cannot figure out the acronym. One is Aga Khan Medical University, one is Qaid-e-Azam University, ComSet's Institute of Technology, University of Punjab, and Alamos Lahore University of Management Sciences. So they all have some physical sciences part, and our publications are supposed to be high quality, and we ranked number one this way. Then we have another program which is very similar to ICTP program of having the visitors, but adopting to the ground realities in Pakistan. We can have somebody as a visitor, who's we call adjunct faculty, a senior person. It can be a visiting scientist or a researcher or a research scholar. That can be foreign or local, having a PhD, visiting NCP for up to a year. Then we have something like an NCP associate, like we have in ICTP, postdoctoral fellows, postgraduate students, and internees. So these are different categories of hosted researcher. I think, okay, I have one more slide. This shows actually our main workforce. These are the graduate students you see. For example, in 2018 alone, there were 167 graduate students working at NCP. They were actually getting a degree from other universities in Pakistan, any other university in Pakistan, but all their research work were carried out under the supervision of the researchers at NCP. I think this is my last slide. Thank you very much. This was the short introduction. Thank you very much for giving me the chance to introduce our center. Thank you.
Thank you very much, Professor Hoorani. So that was really impressive to see. So all the different research that you're ongoing, the diversity of the topic, the number of postgrad as well that you have, and then the capacity definitively with the worldwide scene. So thank you very much. So I don't know if we have a question now, but we may want to keep them for the end as well. And now we can so have our guest speaker, so trying to explain as well what is the power of fire. So if Linn would like to share his screen. Can you do that?
Should be coming.
Thank you very much. It's still very early for you. So sorry. This is
Yes.
one of the commands that we were mentioning at the beginning. We tried to connect the world, so World Wide Web in one sense, and then indeed you had to wake up at 5 in the morning to be able to satisfy the people as well in Australia, in Pakistani and everywhere. So thank you very much for your commitment. So we're listening.
Sure. And I will apologize up front. I find my brain is still trying to, the coffee hasn't kicked in quite yet. So if I sound like I'm slurring my words or bobbling around, I'll blame it on the time of day. So shall I start?
Please go ahead.
Okay, so the first thing I want to do is even though I'm presenting, I do want to acknowledge that that some of the work I'm presenting here has been done by collaborators and colleagues and other people at both Los Alamos and the U.S. Forest Service and other collaborating institutions in Canada and France. So this is aggregated work. So I just wanted to start by getting everyone to think about why we're studying wildfires. I think it's probably obvious to a lot of people, but just to make sure, they're still fairly unpredictable, and their unpredictability threatens people's lives, and obviously their properties. But even evacuation routes are hard to develop because people don't know exactly where they're going all the time. But with that said, they're an unavoidable part of nature. In the US, we've spent over a century trying to put out as many fires as we could and stop them very early. And the downside of that is when you do that, the vegetation builds up and you end up with more fuel, and fires are there anyway. They just come back with a vengeance and become catastrophic many times. So we can't prevent them on the long term. They actually serve a really critical part of the ecosystem processes. So many natural systems depend on fire to stay in balance. And so when we work so hard to put out every fire we see, sometimes our ecosystems get out of balance as well. But even though they're unavoidable, we do hope to manage their effects and avoid catastrophes. Maybe that means putting good fire on the ground to avoid bad fire, or creating fuel breaks around communities, or simply getting people out of the way if the fire is coming. So fire in general, or combustion, has been studied for a very long time. And so many people assume that we already know what we need to know to address the problems in wildland fire behavior. But the reality is wildland fires are different phenomena than structure fires in many ways. And so here's a few of them. So there's a wide range of length scales that are really important for wildland fire behavior. And those range from flame sheets, which are 1/4 of a millimeter, to weather scales and everything in between. And so when you think about the number of different things that are contributing to the behavior of fires, it's daunting to capture them all in computer programs, for instance, and it's daunting to capture them all in our models. Another challenge here is that there's a lot of different highly coupled physical phenomena, everything from complex chemistry to atmospheric dynamics, which we're all, we're getting better and better at, but now we're talking about dynamics at the tree scales, all the way from landscape and global climate down, or global circulations down to tree scales. So there's a wide range there. Multi-phase turbulent flows. So we've got this complex environment where we've got vegetation that's scattered around, and we've got airflow moving in and around the vegetation. It makes it a very complex environment for predicting the heat transfer and therefore the ignition. And one of the things that's really important here to consider is when we do many forms of science and physics in general, we like to be able to validate all of the models that we develop all the way down to their details. And when we think about doing detailed validations with observations, wildfires are particularly challenging because of this wide range of length scales and because of the complex environments that they burn in. Doing a wind tunnel of a small fire is not the same as doing as the phenomena that exist in a full-blown large-scale wildfire. So I think this is something to keep in mind, is we've got to continually work on meeting the challenge of how do we observe these phenomena in a well enough constrained way that we can make sure that we're doing the justice on the modeling. So a lot of what I'm going to show you today is the result of modeling. So I wanted to say just a brief couple words on that. So physics-based or process-level modeling of wildfires is an attempt to capture all of the different pieces and parts and constituent processes that make up a wildfire. And so it's not just modeling the fire as an entity that's moving across the landscape, but trying to capture the radiation heat transfer, the convective cooling, the convective heating, the dependence of the combustion on the mixing and the presence of oxygen. So by trying to capture all these different pieces into a model through partial differential equations, we're hoping to get the essence of wildfire behavior. And thankfully, we've been really excited about over the years about what kinds of things we're able to capture and how they compare to what's observed in the field. So let's step in and just think about predicting fire and about the simplest scenario that we could come up with. And let's start with grass that's homogeneous, relatively constant winds, and flat topography. What I'm showing here on a picture was an experiment that was run by Craig Clements out of San Jose State University back in 2006. So when we think about predicting fire in even this very simple scenario, right, just a grassland, it's flat, we should be able to do that pretty easily, right? Most of the existing operational tools globally assume that if you know the local fuels, local winds, the moisture, and the slope in an ambient sense, you can predict the fire behavior. And I've got a picture here from Phil Cheney and Sullivan's book on grass fires, and these are 3 different fires that were lit at the same time. They all have the same topography, right? It's relatively flat. They're all in the same fuel bed. They're all so they all have the same moistures, etc. Yet they're obviously burning very differently. And so what this picture really drives home is the fact that the processes that drive wildfires go beyond just the local conditions. And many of those processes are actually governed by the way the fires interact with the atmosphere around them through the fluid motions. So I've got 2 simulations now on the screen. These are with a tool called FireTech, which is a couple fire atmosphere model running at meter scale resolutions on supercomputers. And these compare well with observations in terms of spread rate. But what I'd like to point out here is these 2 simulations are identical, except for the length of the line from which they were ignited. And so if we think back to what's in the operational tools or the models that are used by fire services currently to predict the spread of wildland fires, the length of the line doesn't show up in their formulations at all. And so here's something where we have to back up and say, okay, these have the same ambient conditions, but the fires are spreading at very different rates. Why is that? And so the answer is that this has to do with the fluid dynamics that couples the fire to its surroundings. So I'm going to show you one example of this, and this is at the fire line scale, or at the overall fire scale. So I've got 2 pictures here, and these are both grass fires, similar to the ones I showed just a second ago. And these are there's a 400-meter line on the left and a 100-meter line on the right. And we've got streamlines. These are 2D streamlines close to the ground in a 3D calculation, which has some complexity to it in itself. But I think that the message is still really important here. The streamlines, the white streamlines that are coming in from the left, approaching the fire as it moves from left to right, they change depending on the shape and the size of the fire. So if you're not familiar with streamlines, you can think of these as very similar to a river. When a river gets really wide, typically the flow of the river slows down. Where if a river gets narrow, it typically is speeding up. And the streamlines are very similar in the sense that when the gaps between the streamlines, hopefully you can see my mouse. When the gaps between the streamlines is small, the flow is coming fast, and when it starts to widen out, it means the flow is actually slowing down or getting less volumetric flow per unit area. And so what we see is that as the flow comes in, these streamlines are bent by the upward motion of the fire on the flanks. It's getting drawn into the flanking edges. Some of the winds come straight down and hit the front of the fire. This is where it's spreading the fastest. But this divergence of this flow that's coming from the back of the fire means that less air and less kinetic energy are getting to the front of the fire to push it forward. If we go to a smaller ignition line with tighter curvature of our fire, we see that as the flow comes in and it's drawn off to the flanking sides, far less kinetic energy and less wind is getting to the head of the fire. The result is that the head of the fire in a shorter fire or a fire with a tighter curvature spreads slower. And so this is the kind of thing that we need to think about as we move forward to faster running tools. Another example of this coupling that's really important is to think about just the simple models that have historically been used to capture fire behavior or to try to capture fire behavior. The wall of flame concept that first of all, the news media would love to talk about the wall of flame that's coming in the wildfire. But modelers also would like to use this concept because it simplifies the conceptual models that people want to use. It makes computations much easier. Unfortunately, if we look at the fire at the bottom of the screen, this fire is not really a wall of flame. I'm not sure if you can, so let me find my camera. So it's got these fingers, but between my fingers, there's the gaps. And those gaps are really important because they allow the wind to come through that fire line and penetrate and move heat forward. So there's a simulation playing on the right of the screen right now. What you see is a fire that's approaching the viewer, and there's a plane lined with that white line in which we're mapping the wind velocities. And the colors of the winds are indicating the speed of the wind perpendicular to the plane. So in this case, red is out pushing towards you strongly, and blues are where the wind is being drawn back towards the fire. And so you see the character of the wind as it approaches that plane changing dramatically. So we've got a large cell, but then as the fire approaches, it breaks down into these towers and troughs. And the towers are where those hot gases are being driven upward. But the troughs in between the towers, or the locations where and I'll let it play through one more time, the troughs or the locations in between those towers are where the hot gases are coming through the fire line and actually getting to the unburned fuel in front of the fire. So this is not a wall of flame in concept. Instead, it's like a comb where the spaces between the towers of hot gases that are rising are just as important as the rising gases. And so we can see this changing character of the wind field as the fire approaches. On this lower plane, we're showing convective heat exchange. So red being positive where you're heating fuels, and blue actually being where your wind is cooling off the fuel. So keep in mind, in front of the fire, we've got radiant heat transfer that's trying to heat it up as well. But this convection is a dominant factor. So if we're going to predict the way fires behave, it's really important to capture the balances between these processes, which depend on the nature of the fuels, That's not just how much, but actually the structure of the fuels, the winds, and that's not just the mean winds, it's also gusts and fluctuations, as I'll show you in a minute, the moistures of the fuels, and of course topography. But it's especially important to recognize and capture the influence of that dynamic interaction between the fire and the atmosphere. So let's dive in a little bit deeper and just talk about the fuels a little bit. So wildland fuels are different than what we think of as structural fuels. And so this is one of the reasons why I mentioned that structure fires are different than wildland fires. And it has to do with not only the link skills that are influencing them, the size of the fires, but also what they're burning. So if we look at the fuels on the top row, the two top pictures here, those are typically things that might burn in a wildland fire, whereas the things in the bottom are, and so it's key to, when you look at these, to think about what are the differences. They might even be the same exact material, but their configuration is substantially different. And winds interact with fine fuels much different than they interact with the larger fuels of boards or sheets of wood, for instance. And a lot of that's through the boundary layer, the fluid dynamic boundary layer that sets up over those fuels. So just to drive this point home a little bit more, this is Jack Cohen. He's at the Missoula Fire Lab in Montana in the US. And Jack is performing an experiment here where he's got some pine needles and he's putting them in front of a radiant heater. And at time 0, he pulls the tinfoil away and exposes those fuels, whether it's pine needles or grass in the lower right, to the radiant heater to see when they're going to ignite. So in this case, instead of pine needles, he's using shaved wood and a block of wood for the same experiment. So on the bottom, you can see, or on the right in the time series plot, you can see what effect this has when you put these two different kinds of samples in front of your radiant heater. And so the red, go ahead.
Question, sorry, Rod. So would you mind maybe if you want to use your pointer? So
Sure.
to select at the bottom left of your slide, voila, the laser pointer, the laser spot, so like this we can really follow what you're saying.
Okay. Does this work? Can you see my mouse at this point?
Yeah. The laser.
Okay. So this is the shaved wood. So these two different samples were put in front of the radiant heater that we showed you on the previous slide. And so if we look on the right, and we can see as time goes along, we turn on our heater, our temperature starts to rise, and the block of wood, which is the red line here, the temperature continues to rise. There is some natural convection cooling, but at some point it ignites and then of course continues to rise after the exothermic reaction starts. The shaved wood, on the other hand, starts to rise, but at some point well below the ignition temperature, it levels out and more or less stays the same constant temperature. And so the important thing here is to recognize why that is. And that's because of the convective cooling, the natural convection and forced convection that shows up when those fine fuel particles start to rise in temperature. So this is why, if you think of a campfire that many of us have stood around, you can have grass that's really not very far from that fire that never ignites. But if you stand that same distance away from it, you very quickly might have to back up because it's getting way too hot. And the difference is because the air moving over the grass cools it off much more efficiently than the air moving over your legs or your arm, for instance. So, so if we're going to think about fire on a landscape scale, hundreds of meters or kilometers or tens of kilometers, we can use models to explicitly capture some things, such as the movement of air over topography, the movement around large-scale vegetation structure like trees, the large-scale buoyancy influences of the fire. But we have to recognize that if we're going to use simulation tools like that, we can't resolve everything. We can't explicitly capture the flow around a pine needle, for instance, at the same time as when we're going to do something, flow over kilometers worth of landscape. So there's a need to do some subgrid modeling. And on the right, I go back to the same cartoon that I've already used in this talk, but now I've put this grid over the top of it, and it's representing a computational grid that might be used to discretize the physics here. And so when we talk about subgrid, we're talking about things that might be smaller than our computational grid, for instance. But that's also potentially smaller than the data that we have. So if we think about vegetation data or winds, we might know where the trees are. We might know some gross characteristics of the trees, but we definitely don't know where every pine needle is, or even where every branch is, or every gust in the wind at those scales. So it also makes sense to be using something a little bit more stochastic in our modeling of things below those scales. So if we now look at vegetation on a slightly larger scale and just think about the heterogeneity, not only are all those fuels particles associated with the needles and twigs and the blades of grass, but we also have very different structure of vegetation on many of our landscapes. And that structure affects the aerodynamic drag as the wind tries to move through it. It affects the way convective and radiant heat transfer warm the fuels as a fire approaches, or cool the fuels in some cases. It affects the moisture exchange, and of course, it affects how we mix oxygen down and the reaction rate. This is truly a multi-scale, multi-phase fluid atmosphere, fire atmosphere interaction with these fuels. So here's a simulation that was performed by Francois Pimont at INRA in France. I really like it. It's a slice. It's a 2D slice through a 3D simulation where Francois's purpose was to do some validation of the wind fields that we were getting with a coupled fire atmosphere model. And you can see the 6 plots at the top here are comparisons of the wind field at 6 different locations associated with these black arrows at the very top of the screen. So he's comparing the measured winds based on tower measurements with the simulation, and it does pretty well. But the part I like about this a lot is the fact that it drives home the fact that, first of all, these flows are very dynamic. You can see in the movie, the wind speed is at any moment. You've got gusts, but the influence of the fuel break, right? It's just as the cartoon shows at the top of the screen. There's trees, a gap, and then trees again, highlighted with this black line. And there's a really interesting thing that happens here. When we take fuels out of the landscape, we increase the flow rate at that same time. So the So by putting this fuel brake, we actually speed the air up on this downwind side. And so by speeding the air up, we actually might intensify the fire at that location. And so there's a lot of unintended consequences that show up when we start manipulating vegetation that we need to think about. Here's a simulation where fire's moving in under a forest, the ponderosa pine forest, based on some data from Flagstaff, Arizona. And what's being shown with the colors is convective heating and convective cooling. So for those of you who aren't familiar with the term, convective heating is where you've got really hot gases moving over cooler fuels and heating those fuels up. This is a dominant heating mechanism in wildland fire. I'm going to back it up and come back at it one more time. And convective cooling is when you have cool air moving over a warmer surface, or in this case, warmer fuels, which pulls energy off. So convective cooling is what you feel when you're out in a cool breeze, and that's actually, the convection is therefore responsible for, if you're going to have a tree survive a wildfire, a lot of times it's surviving because of that convective cooling that's coming in behind the fire and keeping that temperature at a minimum, just like we were looking at with the fine fuel particles that Jack Cohen was measuring earlier in the presentation. So I'm going to shift gears a little bit and just talk about some influences of slope. And again, I'm focusing on the interaction between the fire and the atmosphere. In this case, I'm going to show you a series of simulations, and each one of those simulations we've accomplished by simply aligning the computational domain with the slope of an idealized very long slope. And so using that technique, here is a series of different slopes: 0 degrees, 5 degrees, 10 degrees, 15, 20, 25, and 30 degrees. And it's important to notice that these pictures are all taken when the fire is at the same location. But if you look at the times 382, 332, 286, all the way down to 130 seconds, you can tell that the steeper slopes, the fire is moving much faster. It's taking less time to get to those positions. So not only do I want to draw your attention to the fact that on steeper slopes, the fire is moving faster, but also the character or the shape of the fire has changed significantly. Here's flat ground and a 30-degree slope animations of the simulations I just showed you. And you can see some very significant differences, not only in the spread rate, but in the shape and depth of the fire line. So this is the same set of simulations, now looking at the 10-degree slope and the 30-degree slope. And so let me tell you about the color scheme. The color scheme is the flow basically towards the viewer, which is up, or down into the surface. Blue is down into the surface, and red is up towards the viewer. And so the first thing I'd like to draw your attention to is, as the flow is coming in from the left, you see a series, and hopefully you can see my mouse, you can see a series of paired updrafts and downdrafts. And these are paired vortices, effectively, right? So you've got this streamwise vorticity that's causing these updrafts and downdrafts to pair up as the flow comes towards the front of the fire. And so, as we saw in the movie earlier, at low slope, the winds are coming from behind the fire, they're penetrating through, and they're pushing heat through the fire line, through those towers and troughs into the unburned fuel in front of the fire. And this is the way that the fire spreads on these low slope scenarios. If we shift over to the 30-degree slope, which is a pretty steep slope, we still have that same behavior of these coupled streamwise vortices where you can see the downdrafts and the updrafts paired, but it gets much more complicated as it moves towards the head of the fire, and this distance or the depth of the fire gets much larger. And that distance, if you think about all what's happening here, there's a lot of hot air that's coming off the surface. And so what's happening is the winds are coming in from the left and they're getting pulled up, and much of that wind never gets to the head of the fire. And so it's a different characteristic. The other thing I'd like to point out is the fact that on the left, we talked about how the wind is punching through that fire line to heat the fuels right in front. On the picture on the right, we have something very different. And if you look at the structure, it's almost like a Kármán vortex street coming off the tip of that fire. And so there's a substantially different characteristics about how we're moving energy via the wind to the front of the fire. So if we now look at vertical vorticity, and vertical, in this case, vertical is perpendicular to the plane. For those of you who are not really familiar with vorticity or what it means, you can think of it as the rotation of the fluids around the fire. And in this case, the red is positive vorticity and the blue is negative vorticity. And what that means is positive vorticity is twisting this way. If you put your hands up, I have to be careful because you're looking at things, my hands backwards from what I intend them to. But if you put both your hands up and your fingers are pointed in, your right hand is curling with the positive, that's the red, and your left hand is curling with the negative vorticity, that's the opposite direction, and that's the blue. So if we look at, and I'll play these movies again, if we look at the picture on the right, the flow is being pulled in on the right side and pulled in on the left side continuously. So the net effect of that is to continually tuck the energy back into the fire line and allows, and so as heat's generated on the fire line, it's just moved along the fire line and funneled to the front. So I'll go back so you can see this again. But the picture on the left is far less, has far less consistent vorticity on the outside. It's much more of these alternating pairs dominate the vorticity field, and you don't have that same tucking that's pulling the heat back into the fire line. And so just to highlight this one more time, here we've got the 10-degree slope and the 30-degree slope again, and I've drawn a white line here along the fire line, and this is using pair view. And so what we've done is we've drawn the stream tracers of air that goes through that white line down near the surface. And so on the left, you see, as we talked about before, winds are coming from behind the fire and then punching through the fire line through these towers and troughs and moving energy to the unburned fuel. What's happening on the right is substantially different. Because of the large amount of uplift that's happening here, we're having to draw winds in from outside the fire line to feed that massive updraft. And the net effect is it's always tucking the heat back into the fire line. And in fact, there's a helical pattern that's showing up here as it moves down. So where heat that tries to get away is tucked back down, and that's what creates the that flow pattern that looked like a common vortex straight at the front end. Here's another view of this, and you can see maybe this pattern of hot air coming up and then getting tucked back down and swirled around and funneled to the head of that fire. That's why the fire gets pointed on steep slopes, and that's why it's moving faster. So I mentioned earlier that we shouldn't just care about the mean wind field, but we should care about the fluctuations as well. And here's an example where the mean wind is exactly the same in the two scenarios I'm going to show you. The only difference is that we've added a crosswind oscillation. So the average is 0, but it's just a sinusoidal oscillation left to right on this wind field. So the mean wind is 6 meters per second above the canopy, but one has a side-to-side oscillation and the other one doesn't. And what you find is that there is a significant effect. And I'm going to show you two movies that have just slightly different oscillations. So the oscillation strength on the right is stronger than the oscillation strength on the left. And the period of the oscillation is exactly the same. But what you can see here is that when you add these oscillating winds, you get that different lateral spread perpendicular to the mean wind. And because we're widening the fire out, we're actually getting stronger downwind spread as well as the stronger lateral spread. I'll back up and come at it again. So again, this is an indication that when we think about the wind field that pushes fire and how it's affecting the fire, we need to think about not just the large scale average wind, but what does the turbulence look like? What are the fluctuations? How really fine fluctuations might not matter, but there's a sweet spot in the where the size and periods of those fluctuations really starts to matter. And it not only affects the lateral growth, but it affects the downwind growth. So one of the important things about fire research is thinking about how do wildfires interact with other disturbances. In the US, there's been over the past 20 years, there's been several episodes of significant vegetation mortality due to bark beetles, due to insects. And so there's a lot of people that have become aware that this is likely to change how fires behave in these landscapes. So this is a study that was led by Carolyn Sieg with the U.S. Forest Service. And she's trying to understand, or we're collectively trying to understand, what is this interaction and how much worse are fires going to be in these landscapes where you've had insect mortality. And you could replace insect mortality with drought or climate change or something else that's compromising the vegetation. So in this case, I'm going to show you a matrix of simulations that were performed. So I'm going to tell you a little bit about them before I show them to you. So we have 3 different levels of mortality where 20%, 58%, and 100% of the ponderosa pines were killed by this insect. And there are some other species intermixed, which you'll be able to see in a minute, but the ponderosa pine is the majority of the vegetation on the landscape. There's the red stage and gray stage. And these are the stages where the red stage is you've killed the trees, but the pine needles are still on the trees. So that's kind of what this picture is showing on the lower left, is the red stage. The gray stage is a year or two later when those pine needles fall to the ground, and they're now surface fuels, but you don't have that high amount of aerial fuels. We looked at 3 different wind speeds. So the matrix therefore looks like this. We've got 20% mortality, 58% mortality, and 100% mortality as we go down in the rows. And then from left to right, we've got low winds, medium winds, and high winds. And again, these are the times are different on these different wind speeds. So keep that in mind as you look at them. So the way that we were looking at this was we wanted to understand how these disturbances were interacting. So we used a synergism index, which came out of the medical field, to say if it's 0 synergism, then it's sort of like superimposing the 2 effects, right? You've got some mortality due to the insects, and then you have some mortality due to the fire, and they're just additive. But then we can get a positive synergism where the bark beetle mortality amplifies the effects of the fire. Or we could have a negative synergism where the bark beetle mortality decreases the influence of the fire on the remaining canopy. And so if we look at this, some interesting things pop out to me, and that is that there's relatively low synergism, low magnitude, I should say, when you have low mortality. This is not surprising, but as that we increase mortality, we get more synergism. The surprising part here is that synergism is highest at low wind speed, which is, we always think of fires, we always think of fires being most severe at high wind speeds. Well, they are, but what this is saying is that at high wind speeds, the fire is going to burn and consume the canopy regardless of the previous bark beetle disturbance. Where at low wind speeds, in the red stage, by leaving those needles in the trees, those dead needles, you're creating more continuity of very dry fuels in the crowns, which allows the fire to get into the crowns and move in the crowns when it otherwise might not, and therefore killing the trees that had survived the mortality. If we go to the gray stage now, remember, this is the stage where we've taken the needles and they've all fallen to the ground. So it's several years after the mortality event. We get something different. We get a scenario where, yes, there's still a little bit of synergism at low wind speed, low mortality, but we actually have strong negative synergism at high mortality. So we've actually made it so that the trees, either the ponderosa pine or the other species that survived the mortality event, they're actually more protected from fire than they would have been without the insect attack. So this is really important. So, and a lot of this has to do with the wind interaction with the canopy and what that drives home. So another key thing to think about is the way the winds interacting with the fire drive the movement of flying debris. And the flying debris, also known as spotting or firebrand transport when that debris is on fire, is one of the most dangerous mechanisms for for fire spread, especially when you start talking about the wild and urban interface. And so these flying embers or flying pieces of bark or sticks, these can move hundreds or even kilometers into an urban setting and start new fires where maybe the fire hasn't even had a chance to move into the community otherwise. And so what we see is that on the picture on the left, we see that the firebrands in this flat topography fire line scenario, they are heavily influenced by that tower and trough that we started the talk with. You can see how the firebrands are concentrated in those filaments that are rising. But when we put it on steeper topography, the shape of the topography, local shape, determines how concentrated and how focused those uprise patterns are. So for instance, on this fire right here, where you've got a ridge, you can see that a lot of these firebrands are being focused into a really strong updraft on the ridge line. And so that affects how high and how far those firebrands go. So we need to think about that. Thinking about, if we're going to think about fuels mitigation or think about preventative measures affecting fire spread, a lot of times we want to go out there and put a fuel break, for instance. And that's great. And that might even stop your continuous fire spread. Here we've got a fuel break in the bottom of the canyon on the bottoms, in the bottom simulation. But those fuel breaks may or may not be effective if you have significant spotting. So in these simulations, the blue are firebrands that are lofted, and the white are firebrands that landed. And in this simulation, we don't have new fires being ignited by those firebrands that have landed, but the concentration of the white dots on the landscape should indicate the opportunity for new fires to start. And so in this case, the fuel breaks does make a significant difference in the ability for those firebrands to start new fires downwind of this canyon. So fluid dynamics and the interaction between the fire and the atmosphere also plays a really big role in some low frequency but very high consequence events. And in this case, we're looking at a downwash event, which you could think of it as a thunderstorm outflow, for instance. And so the picture on the left is a density current that's being formed from a collapse or a downwash event, and you could see that backspinning motion as that density current moves across the landscape. On the right, the two pictures on the right, here and here, this is that density current, which is just slightly more dense air. It's just a couple of degrees difference in the temperature of the air, but it has this backspinning motion as it moves across the landscape. And that backspinning motion associated with, again, a thunderstorm outflow, for instance, when it interacts with the fire, what it does is it has this swirling motion, this vorticity that drives high velocity air down to the surface and continues to push it down. And the net effect of that is to speed up the fire a lot and stretch out that fire line. And so by understanding more about how those kinds of events intensify fire behavior, we can anticipate things a little bit better and hopefully avoid disasters where people are hurt. so I just wanted to mention the fact that the interaction between the fire and the atmosphere is really critical when we start thinking about the interaction between multiple parts of a single fire or the interaction between two fires. Here was an experiment that was run in Spain by Professor Vega, and in this case, the interaction between these two fires, and this is a technique that's oftentimes used to stop fires that are moving. You light a fire in front of it, let it burn back into it, and when they interact, they pull on each other, and the hope is that when you light a backfire, it'll creep back into the original fire. Sometimes it doesn't work that well, and in that case, you can end up with disasters. So the transition, if we start thinking about how multiple fires interact, this brings us to prescribed fires. Because prescribed fires are oftentimes lit with multiple ignition lines, with the idea that those multiple ignition lines are going to interact with one another and affect the way the vegetation burns. This gives the practitioners or the firefighters the opportunity to engineer or control the intensity of the fire by deciding how far apart the fire lines are and whether or not they're going to close the gaps between them on the ends, for instance. And so if we're going to simulate this and help with prescribed fire activities, there's some really critical things. We've got to capture that interaction between the fire and the atmosphere, because that's how those multiple fire lines and complex ignition patterns interact. We've got to capture the three-dimensional forest structure or vegetation structure. For instance, in this simulation, the presence of this road really affects the wind flows that are being drawn back into the fire. And the presence of this road really, and you can see it most heavily on these areas that were shown unburned right in here, it affects the indraft that's being able to be drawn in between these fire lines, because you have less vegetation drag. For prescribed fire, one of the biggest hurdles is oftentimes smoke, because you can't light a prescribed fire if you're going to smoke out a community with people with lung problems, for instance. And so there's a lot of different ignition techniques that can be used to adjust the plume behavior. And so thinking about that coupled fire atmosphere interaction through fluids is key to optimizing the smoke movement along with the fire behavior. One of the things that was really interesting to think about from a fluid dynamics standpoint when you start looking at prescribed fires. On the left is the wildfire simulation that we looked at before, where the wind is blowing in from behind the fire and pushing the fire forward. And when you think about that, the wind is having easy access to the fire because the vegetation behind the fire has already been burned out. Well, in a prescribed fire, and I'm going to back up and come at this again. In a prescribed fire, because of the way the ignition patterns are lit, the wind is going left to right, but yet my ignitions are typically happening from right to left. And so this makes a very different scenario because the vegetation upwind of the fire is still intact, which changes the fluid dynamics significantly and makes it so it's more like a backward facing step flow pattern as opposed to the wind being able to penetrate in and drive the fire forward. So all of this, most of the simulations that I've shown you so far, including the one on the upper right, which you've already seen, they've been done with very computationally intensive CFD-based models, which aren't necessarily the most practical thing for fire agencies to use. And so one of the questions that we've been wrangling with at Los Alamos is, how do we take what we learn from those complex simulations, such as the upper right, and how do we take the essence of that and put it into a tool that practitioners or planners can use? And so, the things that we realized we really need to key in on was getting that coupled fire atmosphere behavior, even in a simplified tool, and getting the three-dimensional structure of the vegetation. And so this is going back to some of our prescribed fire simulations and looking at, here we've got 5 lines of ignition happening. And the question was whether or not, with our simplified tools that have just been developed in the last several years, whether or not we can capture the interaction between the fire lines, because that's critical and it depends heavily on the fire atmosphere behavior, and whether or not we can get things like the heterogeneous consumption of the canopy. And if you look closely here, there's areas of the canopy where we've got, some consumption, and a lot of areas where we don't. So those are very encouraging results. And I think I'm just about done, but I wanted to show you some examples where the New Jersey Fire Service has been asking us to use this new fast running tool to look at their prescribed fires. And in this case, they actually want to burn off a lot of their canopy fuels. In many cases, you want low intensity fires, but in this New Jersey case, you want to burn off a lot of the canopy fuels, not all of them, but a lot of them. But you can see in these, so this is just aerial ignition. This is where you use the helicopter. I'll come back at it because, or this is ATV. This is where they're driving ATVs across the landscape with 5 lines, letting them burn. And this is aerial, where they're doing a Z pattern to light the ignition. And one of the things about that Z pattern is you can see the fire draws in the heat, the different fires as they coalesce. So the New Jersey Fire Service was interested in how much residual fuel was left, but they were also really interested in the fact that in this particular dynamic wind field, this was taken off of real tower data, you had a spot. You see where the fire right here got outside the fire line, and it's creating a wildfire that's causing them a different problem. And so they're really interested in backing up and saying, well, what makes the difference and what changes? So they asked us to do a sensitivity study. These are all the aerial ignition. You can see the helicopter ignition pattern as it grows, but and on the upper left is the scenario I showed you a minute ago, but on the lower left you have decreased fuel load, and on the lower right you have increased moisture content on the surface. And so using these kinds of models with that coupled interaction between the fire and the atmosphere, we have the ability to do sensitivity analysis and look at how things are going to change. And one of the things that people don't always appreciate is how fast those conditions change during the day for either a prescribed fire or for a wildfire scenario, where the surface moisture contents can change dramatically, going from maybe it won't even spread at 9 a.m. to at 11 a.m., the fire will spread with a high intensity, just based on diurnal cycle and the solar angles. So being able to think about that is really important. And I think what I'd like to do is, we can come back to these if you choose, but what I wanted to sort of finish with was a notion about the use of models and the use of process-based models in wildfire research. And it's something that I first heard explained by Sheldon Teese at Sandy National Labs. And I think it's an outstanding point, is that fire experiments or observations of wildfires on the landscape, those are complete physics. They're the real thing, right? They're full scale, but they're only partially disclosed. And what does that mean? That means it's really hard to actually, if you look at that fire on the right, it's really hard to capture all of the different things and the different physical processes that are going on in these fires and measure them. So they're only partially disclosed. We only see part of them. Coupled fire atmosphere behavior models or process-based models, on the other hand, they're only partial physics. There are things associated with the combustion or the flame sheets or the multi-phase flow that we're having to model. And we're leaving some things at fine scales, for instance, out. But the good thing is that what we have is completely disclosed. So we can dump out, we can look at all the interactions between all of the variables in these simulations as a function of time or space. And so the complementary opportunities for these field observations and the modeling are extraordinary if we use them in the right way. We shouldn't trust models without experiments, but the experiments don't necessarily get us all the way either. So models can be used to help us test our understanding, develop hypotheses, look at sensitivity explorations, but it's always really important when we're using models to keep in mind what the assumptions and the approximations are and know the limits of what we're doing. And so I think with that, I'll leave it. Fire behavior is dominated by the motions of the atmosphere around it. The fire influenced wind fields is how we connect the fire to how the fire is connected to its environment to a large degree. If we're going to do better predictions, we've got to focus on this coupled fire atmosphere interaction. And without capturing these feedbacks, we're not going to have robust predictions across a broad range of regimes. And I think with that, open it up for questions.
Thank you very much for this comprehensive and very hot topic. I will have a lot of questions, but I want to make sure before that we have our audience and Hoorani will take over the question that were already popping out since the beginning of your presentation.
Rod, thank you very much for a very excellent talk. It was very interesting. And we already have a number of questions. There are 3 questions I see in Q&A. Can you look at Q&A or?
Maybe.
Or I can read it for you as you like.
Why don't you go ahead and read it?
Okay,
no.
I can read it. So one of the questions is from Vedran Husted. The question is, which scales do you see as the most important for modeling of wildfires? From my experience, meteorologists uses advanced models for the atmosphere and simple flame spread models, where fire scientists tend to use simple atmospheric model and advanced fire spread models. Combustion. Did you get the question?
I think I understand the question. So it's a very good question, and I think unfortunately there's not a clean answer because I think it depends heavily on the fire event. There are fires, for instance, some of the fires in California, I think you can get away with fairly simple fire spread models because it's so heavily driven by the weather events. But in other cases, the fire spread is creating its own local circulations that are far more impactful than the larger scale flow field. And so in those cases, you need to have really detailed coupled fire atmosphere models. So I think it heavily depends on the fire regime and on the types of fires that you're focused on. If you and a good contrast is if you're looking at wind-driven fire events, the large-scale atmospheric flow is really, really important. But if you're looking at prescribed fires, for instance, which are typically lower intensity and slower wind speed, now having a detailed model that captures the fire influences on the atmosphere and the structure of the vegetation's influence on the atmosphere at those small scales is more important.
Okay. I hope this answers the question. The next question is from Conrad Wilkin. How do you judge model complexity versus uncertainty? Or in other words, how do you know when your model is detailed enough but not detailed to make it unusable?
This is also a very good question. So I think certainly we need to separate the uncertainty in the model, which all models have some uncertainty, versus uncertainty in the inputs, which makes it even more complex because many times the information that we're feeding these models has a significant amount of uncertainty in it also. And for that part, we can do sensitivity analysis with the models to see how sensitive we are due to inputs and so forth. But I think doing a lot of the best thing would be if we had great experiments, but the number of great experiments and the diversity of scenarios in which those experiments have been done is rather limited. So the next step is you start doing different comparisons between models of different complexity levels to try to dissect. And the models all have slightly different assumptions and slightly different ways of approaching things. So the hope is that you can start to sort out what the trade-offs are with making different simplifications. It's a fantastic question, and it's a field that's not solved yet.
Okay, so from the same colleague, we have another question. Classic flame spread is generally split into opposed flow or concurrent flow. What about wildfires? Seems like they could be both.
I think they are both. I think it's definitely both.
So then I have a question from Luis Leiner. With regards to model, are you sufficiently satisfied that the relevant physics is included and computational resources to track them with confidence, or are still things to develop at the theory and or technology levels?
There are definitely still things to develop. I mean, we've been really happy with the progress that's being made in the field, but there is definitely there's definitely a lot of things that we would like to be doing better, and especially as we look to address questions in a broader and broader range of fire scenarios. So there's a lot of room for improvement.
Okay, then I have a question from NCP, from Dr. Mohsin Siddiq. I'll try to decipher his question. When you model this dynamics for flow Is it appear in the form of partial differential equations or in discrete variables or mix of both?
So the majority of what's being done in the modeling, such as I've shown you today, is as the majority of it is in the form of partial differential equations. The simpler approaches, the quickfire stuff that I presented at the very end, was used some more discrete variables, and but the majority of the work has been partial differential equations.
Okay. Then from same colleague, there is a question: do you also study chaotic phenomena while making simulation, as the dynamics is so complex?
So this is also a very good question. We actually have a research project being at Los Alamos, being led by Alexandra Jonko, that is that's focused on that chaotic behavior, and that's jointly with Kara Yednick at the Forest Products Lab in the part of the USDA Forest Service in the U.S. But they're focused on exactly that question: when does fire behavior become chaotic? And it is especially true when you start to get sort of at marginal conditions, where the fire is very close to burn, no burn, for instance. You get very chaotic patterns, and where if it's strongly wind driven with low fuel moistures, for instance, it's less of a chaotic pattern.
So this was the last question, but I like to encourage my colleagues to ask more questions. While they think of questions, I was watching you speaking, and on all your slides, you have Los Alamos written. So it actually reminded me of 1984 and 85, when I was a young graduate student at Simon Fraser University in Vancouver, British Columbia. And at that time, I happened to write a code for the quark-gluon plasma, which I tried to run on the computer, which was available at the university, but it did fail. But with the help of some colleagues like Dan Strotman, Byron Jennings, and others, I got access to Cray computer at Los Alamos. So my graduate thesis, I owe to this particular lab and their computing infrastructure, because there it was possible to run it because I was colliding two heavy nuclei using the computer code. This is why I'm very grateful to Los Alamos, even now.
Dan Strotman was the deputy division leader when I was in theoretical fluid dynamics group. So he's a very good guy.
Yeah. Are there any questions?
There are two more questions they're from the panelists, if you look at the chat. So one for Rosenstein and one for Noki.
Yeah. So the one more question from Rosenstein. What happens as the atmosphere surrounding the fire undergoes a transition to turbulent flow?
So of course, turbulence, what is turbulence flow and where is it turbulent, where is it laminar, has to do with the length scales that you're looking at, of course. But the large scale turbulence in the atmosphere has a big effect on the way the fire spreads and the patterns that it forms. But the smaller scale turbulence, of course, has a lot to do with the mixing that contributes to the oxygen getting into the fire and the combustion process itself. So I think the turbulence, the turbulence at various scales matters a lot. And one thing to keep in mind is that the flow through and around the vegetation itself creates a lot, at a minimum, it's creating unsteady flow. And some people would say in some cases that's actually creating turbulence before it even gets to the fire.
Okay. And then I have another question from Naoki Iwamoto. I apologize if I'm mispronouncing the name. In extinguishing wildfires by spraying water from above, how do you estimate the amount of water you need and how you spray? That means the density. How do you take into account the effects of water in extinguishing the fire?
So we haven't put a tremendous amount of effort into addressing that particular question. It's a very good one, and it depends on whether or not you're using the hose or whether or not you're doing drops from a helicopter or a plane. And if you're doing drops from a helicopter or a plane, a big question is just how much of that water or even retardant actually gets to the surface, because a lot of it is evaporating if it's moving through a dry atmosphere before it even gets to the surface. So that's as much of an atmospheric dynamics and moisture question as anything else. But the minimal amount of work that we've been doing with it is just to look at the effect of locally increasing fuel moisture, et cetera. But we really haven't spent much focus on that question.
Colleagues, are there any more questions to the speaker?
I would like actually indeed to know a little bit more as well. So with your CFD, with the calculation that you're doing, so you're doing mass conservation, the energy conservation, and then the momentum conservation. That's mainly with the Navier-Stokes and all those aspects, taking into account the turbulence, isn't it?
Right.
In your PDE. So this is what you have. So
we've got first, go ahead.
And then to understand it, looking at this, then the stability, are you using different stabilization technique, artificial diffusion, or anything that could find ways to make a faster converging? Because this is with this computing capacity there where you could gain potentially. So with then, the next question will be like with the high performance computing. So are you using, and I guess that this is exactly so what Professor Hoorani was mentioning, the capacity that you have there in Los Alamos definitively is great, but you could certainly do some better simulation as well. And the difficulty there is as well, so you have the characteristic time, which is one thing to really work well with, and then the element. So when you think in terms of you think about the atmosphere, so the meshing or the way you have really to tune all of that so that it can give you as well an accurate and a good simulation. So this is the tricky part, I guess, that you.
It is, and there's a lot of room for multidisciplinary advancement of this field. I think the efforts that we have done here should be thought of as opportunities for collaboration, in my opinion, because there's a lot of, you just pointed to a whole range of things that we've talked about using artificial diffusion. We've talked about, there's always efforts at Los Alamos to improve our atmospheric modeling for a variety of reasons, but there's a lot of room for collaboration and interaction there. So we are solving partial differential equations for mass, momentum, and energy in a fully compressible approach for the atmosphere. And then we're also doing partial differential equations for the solid, for the amount of vegetation that's there, for the temperature, and for the moisture content of the vegetation, as well with convective heat exchange and aerodynamic drag as the connections between the momentum, the solid and the gas phase, and a Monte Carlo radiation scheme for the thermal radiation as well.
Okay, so you're already accounting for quite a lot of multi-physics phenomena. But
we're trying, but it could all be improved. I mean, it's in many cases what we've done is we've over the past 20 years we've tried to add and improve bits and parts and pieces here and there, but especially when we start talking about the subgrid modeling, there's a lot of opportunity for continued improvement as well.
So definitively space for more collaboration, as you said. So with
Exactly.
University, potentially as well, with Professor Patanka. So maybe
Yes.
I don't know knowledge Patanka. And
Yes.
then with, so in Lund, so the first question was raised as well from Professor Husted in Lund University. And they do a lot of simulation. And as well as you said, the importance of simulation and real life validation as well, and try to see as well with all the simulation and all the possibility to make some imaging, then correlation, then potentially machine learning, then potentially as well developing some way of novel thinking that could help. Then when you would think like by having a view of those development of the fire just by a plane, for instance, you can already pattern something that already happened and try to understand what is the best way to limit or to minimize.
You're exactly right. And I think this is an opportunity. There's a big opportunity here for machine learning and AI to contribute. We've been working very closely with the University of California, San Diego, and actually this is part of Alan's doing to bring in the machine learning and AI experts from UC San Diego to help contribute to the advancement of science in this area. I think it's a huge opportunity space.
Right. I still have one more question coming from Pakistan, from Dr. Ashfaq Ahmed. How do you validate your models? Are these models always describe actual fire dynamics?
So I'm not quite sure that I understand the question. Could you repeat it one more time?
How do you validate your models? Are these models always describe actual fire dynamics?
So as I mentioned in the beginning of the talk, the validation here is particularly challenging, and you could think about validating parts and pieces of it. You could validate the drag model, or you could validate the heat transfer part, or you could validate the model for the combustion. But I think one of the most challenging parts here is how do you validate the composite or the aggregated effect of all these non-linearly interacting processes that create the wildfire itself, and make sure you have the connections between all these processes correctly. Unfortunately, it's very challenging to perform experiments that are adequately characterized to constrain your models in a sense that you're doing true validation. We've worked really hard to compare to grass fire experiments and the large crown fire experiments in Canada, and a variety of prescribed fire experiments that are going on across the US. And we're working with some people in Europe to try to simulate some of the fires that they're observing. I showed the work by INRA to validate the wind flow, the canopy wind interaction. And so I think it's an ongoing process. And if the question is, do I feel like it's completely validated? No. Are there parts that are validated? Yes. Is there a need for additional validation experiments? Yes. Are they really hard? Yes. And oftentimes very expensive.
Thank you. By the way, right now we are experiencing an extreme weather phenomena. Wind speeds outside is maybe 50 to 60 kilometers an hour, and they are picking up even more.
Wow.
Let's hope there is no power cut. Are there any more questions?
And And we recall that you can send your question to the email, which is just above there as well. Huh? So if you have more questions, and then we will connect as well. So or if you prefer to have questions directly addressed to you. But in any case, I think it's like, as you said, like field of collaboration, open. Yes. On really burning topic definitively, and it will be with this climate change, something that is more and more common, unfortunately. So we need to link our force because physics matters.
Yes.
So I think my role of moderator ends here. I pass it on to you again. Maybe you can conclude it, Christiana.
Thank you very much. So thank you very much. So I think it was very informative and extremely interesting. So, and Alan can also second me, I'm sure, on that. So we will have, so you see those type of, and Luisa is here as well. So Luisa, who is really the spirit of the physics matter. So from the beginning, and I think it's really interesting to find topic of that style that really engage the community. And as we say, just building up for you, but as well in all those developing communities, some expertise. And we had as well, so the second question was raised as well by a student from Australia. So same thing, you know, like developing this know-how and improving, again, with the cloud, but with new ideas. So that's a great action. I like that. And so then, yeah, so we thank you again, so Rod, for your time. So now it's almost time for your breakfast.
Yeah.
Yeah. And then
it's time for dinner.
And for dinner for you, voila, and some soupe indeed for some other person in Australia as well. So then just one next, the next colloquium, so we had, so define it just also lately, that will be so on the 15th of June, that will be on the Sesame time, and this will be held so by so Guian Kamel, so who will speak about the Sesame and the new adventure of the Middle East woman scientists. So this is also where we invite everybody to connect. So more connection with the Middle East and trying to use and to find a peace as well, and physics as a leitmotif as well for that, hopefully. And then maybe so Luisa and Alan can mention about tomorrow, really important event as well that will take place. So thanks to the APS forum. So with more physics, peace and human rights. So Alan, I let you introduce.
Yeah, thanks for bringing that up. Tomorrow is the centennial celebration of Andrei Sakharov's birth. And we will have an expert series of panels that will explore aspects of Sakharov's interests and career accomplishments, everything from plasma physics to human rights. So that can be joined through APS and RASA, which is a Russian-American scientific association, and those links should be available on the APS or the FIP websites. That's tomorrow at 11 a.m. Eastern, I believe. Lisa, do you have anything to comment? Okay.
So then thank you, everyone. And I think that we will stay connected and stay tuned. So with this physics matter and with the fire and many other topics and all as well. So look at the website, where you have already the pre-recorded so conference that were held last year. So thanks to Luisa. And then the coming one as well will be announced in that website. So plenty of recording, and then the sustainability of all of that will be ensured. So this is what we aim at. So thanks again for your participation. So it may be in terms of time, quite some added time, but then I think it's really worth it. And we can sleep a shorter time. This is okay. What is important is really to fix the problem of humanity. So thanks again for being with us, and we will meet very soon then, and hopefully tomorrow already for more science, for peace. Bye.
Thank you.